let us continue our discussion on the hyperbolic model. Let us try to modify so that we can incorporate the effect of constant Poisson's ratio, or after the critical state the Poisson's ratio should approach 0.5, and then we will also see how to determine the material properties in this lecture. So, in the previous lecture this is what we had seen. So, this is what we had seen. This is called as the hyperbolic equation given by Kondener, and this equation was slightly modified for adapting it to finite element implementation. By differentiating this with respect to strain, we can get our tangent modulus, and d sigma by d epsilon is defined as the tangent modulus, and then we have seen this equation. This is another beautiful equation, and this is our original hyperbolic model, and here we are able to represent the effect of sigma 3, that is the confining pressure on the initial modulus, and this and then this quantity that we had seen 1 minus sin phi times the shear stress divided by 2 c cosine phi plus 2 sigma 3 sin phi is actually the mobilized shear strength. This 2 c cosine phi plus 2 sigma 3 sin phi by 1 minus sin phi is our sigma 1 minus sigma 3 failure. So, this is our mobilized shear strength, and in one equation Duncan and Chang, they are able to take care of the reduction in the Young's modulus with increase in the shear stresses, and then increase in the shear modulus because of confining pressure. So, the limit state of stresses through the Mohr-Coulomb relation is also incorporated through this Mohr-Coulomb relation, and the only limitation here is the soil continues to undergo volumetric compression even after the limit state is reached, because we assume the Poisson's ratio to remain constant. Okay. So, that let us try to see how we can incorporate, and this is what we had seen in the previous class. As the shear stress is increasing, your shear modulus will go on reducing. So, initially we have the Young's modulus as EI, and then as the shear stress is increasing, your modulus is reducing, and ultimately it has come down to 0.0225 times EI. Okay. And because our RF is always less than 1, it is about 0.85 to 0.9 or sometimes even 0.6. Because RF is less than 1, our tangent modulus will never become 0. And these are all what we had seen in the previous class, that the hyperbolic model. Let me just get back to laser pointer. Okay. So, our hyperbolic model is also a nonlinear elastic model. That means that the stress and strain are nonlinearly related, and then the unloading will recover all the strain, that is elastic, and it will not be able to simulate the shear induced dilation, and this model is applicable to all the soils that undergo volumetric compression during the loading, and then the Poisson's ratio is assumed constant. So, the soil continues to undergo volumetric compression even during the critical state. So, we need to modify this. In 1979, Duncan and others, they have modified the original hyperbolic model by writing the constitutive matrix in terms of bulk modulus K, and then Young's modulus Et. And the advantage of this is that the Poisson's ratio tends towards 0.5 as our tangent modulus reduces to near 0 and our bulk modulus K remains constant during the analysis, that we will see, and our Poisson's ratio, the tangent Poisson's ratio tends towards 0.5, and because of that we will be able to represent the constant volume after the critical state is reached. And this particular modified hyperbolic model is written in terms of tangent Young's modulus Et and then tangent bulk modulus Kt, and Kt is the bulk modulus that relates the volumetric changes to the bulk stress, volume changes to the bulk stress, and Et is the tangent Young's modulus. And the K is the bulk modulus, it relates the volumetric stresses and volumetric strains, and this particular parameter we can determine from the volume strain data from CD tests. And our Young's modulus Et relates the shear strains and shear stresses, and then the tangent Poisson's ratio nu T is written in terms of our K and Et as 1/2 of 1 minus E by 3 K, okay, and our constitutive matrix between the relation between the stress and strain can be written in terms of bulk modulus K and the tangent Young's modulus Et like this, and our nu T is 1/2 of 1 minus E by 3 K. As E tends towards 0, our Poisson's ratio tends towards 0.5, and our Young's modulus, the tangent Young's modulus is represented by the same equation that was derived earlier, and then the bulk modulus K is expressed in an equation similar to our initial modulus as Kb times Pa sigma 3 by Pa to the power n, and there is no shear failure term here because the shear stresses do not affect our bulk modulus. The shear stresses and shear modulus are related, and then the bulk modulus is only related to the bulk stresses or the volumetric strains, and so the Mohr-Coulomb failure relation is not incorporated in this equation for K. So, if your sigma 3 is remaining constant, your K will remain constant during the analysis, and our Young's modulus will go on decreasing with increasing shear stresses. And in this equation we have number of parameters, the C and phi are the strength parameters, and RF, Ke and M, these are related to the Young's modulus parameters, and then the Kb and N are our bulk modulus parameters, and our bulk modulus K can be represented as the change in the bulk stresses divided the average change in the bulk stresses divided by volumetric strain, or if you relate to the triaxial compression test, we can express the K as sigma 1 minus sigma 3 at 70% stress level divided by 3 epsilon V. This is our mean normal stress, because in the triaxial compression test during the application of the deviator stress, the delta sigma x and delta sigma y are 0, and we have only the axial stress, that is the deviator stress, and our volumetric the bulk modulus is related to the deviator stress at 70% strength level, divided by 3 epsilon v. This right, this is our mean normal stress, because our sigma x and sigma y are 0, and the only normal stress that we have is the axial stress. So, this is our mean normal stress divided by our volumetric strain. Epsilon v is our bulk modulus, and in case we reach the constant volume state before the 70% of the deviator stress is reached, then the K is evaluated when the volumetric strain has become constant, like this. Say in general, our volumetric or the bulk modulus is represented as the ratio of this divided by 3 to volumetric strain at this 70% of the peak stress. If the constant volume state is reached at a very large strain level, but sometimes at very low axial strains itself we might reach the constant volume state. In that case, we use this epsilon v constant and then sigma 1 minus sigma 3 c, that is when the volumetric constant volumetric strain is reached. Okay. This is, in this case, our K is sigma 1 minus sigma 3 at the constant volume strain divided by 3 epsilon v, and we can actually relate the variation of the friction angle with respect to the confining pressure through this relation. Phi is phi naught minus delta phi log sigma 3 by Pa to the base 10, and basically at higher confining pressures our shear strength will reduce, and that is expressed by this equation. As your sigma 3 is increasing, your phi will reduce. The phi naught could be your shear strength at an average confining pressure equal to atmospheric pressure Pa, and at lower confining pressures, so at a sigma 3 less than Pa, this quantity becomes positive because your log of sigma 3 by Pa becomes negative. Your friction angle will increase. At higher confining pressures, your friction angle will reduce. So, our material parameters for this for the hyperbolic model are Ke, M, Rf, C, phi, and then our Kb and N. Okay, and the C and phi can be determined from triaxial compression tests or direct shear test data, and Ke, M and R, Rf are determined from the initial modulus terms and the ultimate shear stress that I will explain. And so basically we have seen a graph between epsilon and epsilon by sigma 1 minus sigma 3, and we said that for a truly hyperbolic behavior, that graph is a straight line. And what Duncan and Chang have done is that you do not need to plot that line based on all the data points, but you select 2 data points corresponding to 70% of the peak stress and 95% of the peak stress, and plot this graph of epsilon versus epsilon by sigma 1 minus sigma 3, and then the intercept will give you the this A, or the reciprocal of the initial modulus, and then the slope is your reciprocal of the ultimate deviator stress. So, basically it is a very simple one, because now instead of using all the data points, we use only 2 data points, one corresponding to 70% of the peak stress and the other corresponding to 95% of the peak stress. And for determining the model parameters, we need to perform the triaxial compression tests at different confining pressures, and the range of these confining pressures should correspond to what we expect in the field. So, if you are dealing with a dam of let us say some 20 meters height, we can calculate what are the operating range of pressures, like 20 meters height multiplied by an average gamma of 20 means that 400 kPa, and if your K naught is about 0.5, then your confining pressure could be of the order of 200 kPa. So, based on some empirical calculations like this, we can decide what should be the range of your confining pressures in the laboratory tests. Okay. And let me illustrate this procedure with an example. And here we have data from 4 different triaxial compression tests performed at 4 different confining pressures of 345, 690, 1035 and 1725, and then these are the corresponding maximum deviator stresses: 1100, 2020, 2935, 4755, and then the maximum vertical stress is basically sigma 1 minus sigma 3 plus sigma 3, 1445, 2710, 3970 and 6480. And then we can determine our P and Q values. P is sigma 1 plus sigma 3 by 2, Q is sigma 1 minus sigma 3 by 2. Then we can plot a graph between the P and Q, P on the x axis and Q on the y axis, and then get the cohesion as 50 kPa and friction angle phi of 34.7 degrees. And this is a very simple thing that we learnt in the advanced soil mechanics courses on the shear strength of the soils. If you do not want to draw the PQ diagram, we can draw 4 more circles and then draw a common tangent, and then we can get these values. The advantage of the PQ diagram is that we can do the regression analysis. We can give this data to any calculator or Excel spreadsheet program and then fit a straight line and get our intercept on the y axis and then the slope, and from that the phi is sine inverse of that slope, and then the c is the intercept divided by cosine phi, and in this case the c is 50 kPa and phi is 34.7. Okay. And then for determining our Young's modulus parameters, our Ke, M and Rf, we need 2 data points corresponding to 70% of the peak stress and 95% of the peak stress. And then here I have illustrated, let us say that this is your peak stress, 70% of this, 95% of this, and then the corresponding strain we indicated as epsilon 70%, that is the strain at a stress equal to 70% of the peak stress, and then epsilon 95 is the strain corresponding to the 95% of the peak stress. And then we can plot a graph between epsilon and epsilon by sigma 1 minus sigma 3, and then get the intercept and the slope, and the intercept is 1 by EI and B is the reciprocal of the ultimate stress, and RF is sigma 1 minus sigma 3f by sigma 1 minus sigma 3 ultimate. Okay, that is this B. And so our EI we need to determine at least at 3 different confining pressures, and then we can plot a graph between log sigma 3 by Pa and log Ei by Pa. So, our equation is I think I have to so our equation for Young's modulus is sorry for my bad handwriting. Okay, I think I forgot to use the pen. I think next time I will use the pen. Okay, but anyway, this is our equation for the Young's modulus, and this we can rewrite as Ei by Pa is equal to Ke times sigma 3 by Pa to the power m, and by taking the log on both the left hand side and the right hand side, we get this. So, if you plot a graph between the log of Ei by Pa and log of sigma 3 by Pa, this quantity log Ke is the intercept on the y axis, and then the slope is your m. Okay. So, our we have the basic data from 4 different confining pressures, and then we can take the 70% stress level and 95% stress level at each of the confining pressures. So, at a confining pressure of 345, the maximum deviator stress is 1100. So, 70% of this is 770, and 95% of this is 1045, and then the corresponding axial strain is epsilon A, and this is epsilon A by sigma 1 minus sigma 3, and epsilon A is 0.04 at 95%. This is your this thing. Then we can plot graph between epsilon and epsilon by sigma 1 minus sigma 3 at different confining pressures. So, this is the graph for confining pressure of 345. I have plotted a graph between epsilon and epsilon by sigma 1 minus sigma 3, and the intercept on the y axis A is this, and the initial Young's modulus is reciprocal of this, that is 89,518, and the B is the slope of this line, that is the inverse of the ultimate stress. So, our sigma 1 ultimate is 1475, and this is the test at 345 confining pressure, and the sigma 1 minus sigma 3 failure is 1100, and sigma 1 minus sigma 3 ultimate is 1475. So, our RF can be determined as 1100 by 1475. Okay. And similarly, at a confining pressure of 690, our A and B are this, and confining pressure of 1035, and in fact, as we see at confining pressure of 345, our initial modulus is 89,518, and at a confining pressure of 690, our initial modulus is increased to 143,317, but then at a confining pressure of 1035, the initial modulus is reduced. That means that there is something wrong with the data, and that's not consistent with what we expect. Okay, but sometimes this is what happens when we do a laboratory test. We may get some value that is not consistent. That could be either because of the sample disturbances or because of the of not following the standard procedures for doing the laboratory test. So, our sigma 1 ultimate is 4945. Okay. Similarly, at confining pressure of 1725, the EI is this, and sigma 1 ultimate is 6765. So, if you look at our the data at 345, our initial modulus is 89,517, 690, 143,317, and our 1035 is 127,895, 1725, 252,161, and our sigma 1 minus sigma 3 ultimate values are like this. Our RF is sigma 1 minus sigma 3f divided by this ultimate value. So, at a confining pressure of 345, the RF is 1100 by 1475, so approximately 0.75. Once again, at 690 it is about 0.75, and at 1035 it is about 0.6, 1725 0.703, and what we do is we just simply take an average value of RF, because we do not have different RF values at different confining pressures in that equation. So, we take an average value of RF and use that same RF at all the confining pressures. Okay. And if you plot a graph between so here this we have at sigma 3 of 345, the initial modulus is 89,517, and this is sigma 3 by Pa and EI by Pa, and then at 690, 1035, 1725 we get different sigma 3 by Pa and EI by Pa, and then we take the log of sigma 3 by Pa on the x axis and the log of EI by Pa on the y axis, and you see that at this confining pressure your Young's modulus is reduced instead of increasing. So, we might have as well omitted this data point, but anyway, just to illustrate, I have included this in the regression analysis, and if you do a regression analysis, we will get an equation like this, and so our intercept on the y axis is 2.6265, our Ke is 10 to the power of 2.6265, that is approximately 423, and our exponent is the slope of this line, that is approximately 0.58. So, if you do this calculation at different confining pressures at sigma 3 of 25, our initial modulus is 19,088. Okay. And so, for this particular case, our RF is 0.7, and so if the limit state is reached, in that bracket 1 minus sin phi times sigma 1 minus sigma 3 by 2c cosine phi plus 2 sigma 3 sin phi, that becomes 1, and so that E tangent becomes 1 minus RF times 1 square multiplied by EI, that comes to about 1718, and that is 9% of the initial modulus. And we can do similar calculations for the bulk modulus, and at different confining pressures, and at 70% of the maximum deviator stress, the volumetric strains from different tests are like this, and our bulk modulus is the mean normal stress, that is sigma 1 minus sigma 3 at 70% divided by 3 divided by epsilon v is your bulk modulus, and then our sigma 3 by Pa is this, K by Pa, and we can plot a graph between log of sigma 3 by Pa and log of K by Pa, and then we get a regression equation like this. and our Kb is 10 to the power of this intercept, that is 204, and n is the slope of this line, that is 0.44. So, our tangent Poisson's ratio is now written as 1/2 of 1 minus E t by 3k. In fact, we are not going to use any tangent Poisson's ratio in the finite element calculations, because we are going to use only the bulk modulus k and then the tangent Young's modulus E t that we get from that long equation. So, sometimes depending on the initial values, our if your k is very small, your Poisson's ratio might become negative. In that case, we reset the Poisson's ratio to 0, and then our E t is set as 3 times the k. In case E is more than 3 times the k, it is reset to 3k, because we do not want any negative Poisson's ratio in our analysis. Our reasonable values for the Poisson's ratio are about maybe 0.25 to 0.45, 0.5. Okay. And just to illustrate, at different stresses, shear stresses, we see that our tangent modulus at the start is 42,653, and our bulk modulus k remains constant, because it is not a function of the shear stress, is only a function of sigma 3, and our bulk modulus remains constant, and then our tangent modulus will go on decreasing at higher shear stresses. So, to start with, our Poisson's ratio is 1/2 of 1 minus E by 3k, E divided by 3 times this, you will get about 0.16, and as E is reducing, your Poisson's ratio will increase. This is what happens. At a stress of 100, our Poisson's ratio is increased to 0.25, at a stress of 200, 0.33, and at a dV at a stress of 455, our stress ratio is 1, that is the sigma 1 minus sigma 3 by sigma 1 minus sigma 3 failure, that is 1. The mobilized shear strength ratio is 1, and our Poisson's ratio is 0.47, which is close to 0.5. So, actually let's just let me show you the Excel spreadsheet program for the modified hyperbolic model. Okay, in this modified hyperbolic model, we have more number of parameters. The C and phi are the shear strength parameters. Sigma 3, let me just do it at 100, okay, and Ke and Pa are 423 and 102, and the exponent for the Young's modulus term is 0.48, and then our E initial is 42,653. Our incremental strain is 0.002 for doing our triaxial compression test. RF is 0.85, Kb and N are 204 and 0.44. Okay, and then the bulk modulus is 20,727, that will remain constant all through, okay, and we can perform the triaxial compression test in the same manner as what we had done in the case of bilinear elastic model, and at each stage we calculate the tangent Young's modulus, and then the incremental stresses is incremental strain 0.002 multiplied by this tangent modulus. Okay. So, basically if you see this equation, C 16 times B8, B8 is 0.002 and C 16 is 42,653, and the incremental stress, and then the total axial stress is previous stress is 100 plus 85, 185, and then as you go along, your tangent Young's modulus goes on reducing, and your Poisson's ratio, initially it's about 0.166, then it has increased to 0.298, 364, and so on. So our Poisson's ratio will go on increasing, and our maximum the limiting axial stress is 407, and let us see. Okay. So here around this 407 we have reached the limit state, and our Poisson's ratio has reached about 0.491, and beyond that also it is changing because our Young's modulus will go on reducing, and you see at the limit state the initial the tangent Poisson's ratio has increased from an initial value of 0.155 to about 0.49. Okay. So that is what, when we look at the volumetric strain graph, it will initially compress at a very fast pace, but then towards the limit state, as the Poisson's ratio approaches 0.5, your the further volumetric strains will not increase much. So your volume strain graph will look something like this, which is almost like our constant volume state, and then the stress strain curve is similar to this. Initial sigma 1 is 100 because our sigma 3 is 100. Then with increasing axial strain we get increasing stresses. Okay. And in this particular case I have plotted only up to 5% axial strain. So at 5% axial strain the sigma 1 is 412. Yeah, sigma 1 is 412, and as we go on increasing the axial strain, the axial stress will go on increasing without any stop. And let me just illustrate at a higher, say at a confining pressure of 100, our limiting Poisson's ratio is about 0.49. Actually it is it's going almost to 0.5. Okay. And the initial Poisson's ratio is about 0.155, and let us see what happens at a confining pressure of let us say 500 kPa. And we see our initial Poisson's ratio is very small, 0.06, and it becomes more and more brittle because the ideal brittle material has a Poisson's ratio of close to 0. So at a higher confining pressure our soil is becoming more and more brittle. So this is what we see, 0.068 for the initial value, and then as the shear stresses go on increasing, your Poisson's ratio tends towards 0.5. So if your the stress strain graph is something like this, initially it will increase very fast, and then after reaching the limit state it will increase very slowly. And the volumetric strain graph also is very beautiful because after limit state your further increase in the axial strains is not much. Let me just oops, no, I think let me just let me just change the limit on the x-axis. What's happening? Oh, I think I how do I change the limits? Data. No, I think I not able to get the change in the x value, but if you plot it the volumetric strain, you see it is it's continuing to increase. Then after the limit state is reached, it is more or less remaining constant, as you can see from the values here 1208, 1209, 121 and so on. It's basically it has reached a constant volume state, and so because we are representing the constitutive matrix in terms of a tangent Young's modulus, that is a function of the shear stresses, and then a bulk modulus, that is not a function of the shear stresses. There is no failure term in the bulk modulus. So our because of that, as the E reduces, your Poisson's ratio will go on increasing towards 0.5. So that is what we see here. Okay. So the initial Poisson's ratio was 0.068, and then quickly it has increased to 0.175, 0.246, 0.295 and so on. And so the other thing that we need to see is our sigma 1 failure should be 1883 as per our Mohr Coulomb relation, but then if we see this the predicted sigma 1, it is much more than 1883. It's increasing to more than 2000. Okay, that's what we see here. So if you look at this, it's you actually have to plot beyond I think I think I will not change this value, but you can do it yourself, like you can increase the range of the x values and plot up to larger axial strain. Then we will see that your volume will remain more or less constant. Okay. So let us just do for one more confining pressure, let us say 200 confining pressure, and here at a confining pressure of 200 our Poisson's ratio is 0.12. At a confining pressure of 100, the initial Poisson's ratio was about 0.15, now it is 0.12. And if I let us say change this confining pressure to 50, so our initial Poisson's ratio will be higher, 0.18. Okay. So we see that this modified hyperbolic model is able to also incorporate the influence of tangent Poisson's ratio on our predicted volume changes, and towards the limit state our volume more or less remains constant. Okay. And the only thing that we notice here is that both the original hyperbolic model, and also in the modified hyperbolic model, the predicted deviator stress is much higher than the theoretical limit. Say for example, for this case of 50 confining pressure, the maximum sigma 1 is 222, but your stresses predicted are much higher than 222. So, that is one thing that we need to fix, and that we can fix by decreasing the incremental strain ratio. We can work with smaller strain increments to increase our accuracy. That is what we had seen with the bilinear elastic model. The same principle works even with the hyperbolic models, and here also we see our incremental stresses are much lower because our incremental strain is only 0.001, okay, and because of that our stress predictions are slightly better and they are more accurate. Okay. So, let us go back to our PowerPoint file, okay. And so this the modified hyperbolic model is able to represent the stress strain behavior and also the constant volume state after the limit state, okay. And it is slightly better than the original hyperbolic model, but then it is also elastic. So, you will only predict volumetric compressions, you will not be able to predict the dilation. And so, this is the comparison between the experimental data and then the finite element predicted stress strain graphs at confining pressure of 345 and then 1725. These are the two extreme pressures. So, our hyperbolic parameters, they were estimated based on only two values, one at 70% stress level and the other at 95% stress level, but still we are able to get a good prediction at all the stress levels. So, that is the feature of this model. The Duncan and others, they have analyzed a lot of data, and then based on that they selected only two data points, one at 70% and 95%, and then they said that you will be able to represent the entire stress strain curve. Okay. So, you get a good match at both the confining pressures using the same K and M parameters, and then the volumetric strain graphs also are like this. This is the experimental data. There is a lot of dilation after reaching the limit state, whereas in the finite element model there is only volumetric compression. So, initially there is volumetric compression, and then after some time, after reaching the limit state, the volumes remain constant in the volumetric in the finite element analysis, because we have not modeled the dilation. So, at a higher confining pressure, because you reach a limit state at a larger axial strain, we see that up to a larger axial strain, we have not reached the plastic limit state. So, we get compression even in the experimental data. Then after this, the volume strains have slightly started increasing, but then if you look at the slope of this line and this line, there are two different values. The slope at a lower confining pressure is higher, that means you get more dilation, whereas at a higher confining pressure you do not get too much of dilation, because the confining pressure is so much that the soil cannot expand much, and this particular one is the finite element predicted volume change data. Okay, after the critical state, the finite element predicted the volume strains, they have remained constant, but then the finite element model is not able to predict the dilation. So that's a slight improvement in the original hyperbolic model, that we are able to predict the constant volume state after the limit state, but we are not able to represent the failure. And at higher strain rates, like if you apply the strain increments at very coarse increments, our predicted axial stresses are much higher than the theoretical limit. So that we need to somehow correct. Okay, that we will see in the next class how to do that. Okay, and before that, if you have any questions, please send an email to this address profkrg@gmail.com, and then I will respond back to you. So thank you very much.